So, hello, my name is Sebastian Gampe, and I'm working for the Frankfurt Big Data Lab in Germany. I'd like to present you the results of our research in the combination of machine learning and ancient numismatics. The presentation will focus on problems and potential of the image and natural language recognition on ancient coin data. We start with a quick look at the implementation of our work. We have combined the machine learning methods of natural language processing and image recognition with a convolutional neural network. The named entity recognition pipeline based on NLP was implemented with the SPACY application programming interface on Jupyter Notebook for Python. The image recognition based on a convolutional neural network was developed with the Caffe API and pre-trained model on Jupyter Notebook. This work here is based on the bachelor thesis of Patricia Klinger and the master thesis of Antje Lurian. So let's have a look at our data. The source of our data is the online coins of the Roman Empire database, which can be accessed online and as a downloadable resource description framework dump. In our approach, the obverses of the OCRE coin types based on the Roman imperial coinage play a crucial role. We use 3 of their elements as input for our workflow. The first one are the coin designs, which describe the iconography of the obverse. The second one is the so-called crown tooth, which is represented by the portrait attribute. The third one are the images of the coins, which are associated with the coin type. So let's now have a look at the general workflow of our approach. The OCRE coin designs serve as input for the NER pipeline. The pipeline generates an output with the type ID identified from the type design and labels for them. In contrast, the crown tooth is not processed in any way. It will be assigned to the NER and IR results by the type ID. Our image recognition can detect up to 5 different portraits and their corresponding probabilities as a result. Every type can have several results depending on the number of associated coins. In the next step, all the results will be transformed from a relational database to RDF dump by the D2RQ software. Finally, this dump is loaded to Apache Fuseki Sparkle endpoint, which allows to do queries for the following analysis. So let's start this analysis by discussing the problems of the NER pipeline. The explainability of NER results is the main problem here. In a few cases, when there are more than one persons in a design, not all persons are recognized by the pipeline. As an example for this behavior, you can see here that our NER model has found the Emperor Crispus and the Goddess Victory in the design. But the Emperor Constantine II was not found. We don't have any good explanation for this now, so we have to investigate further. Let's have a look now at the potential of the NER approach. The main task for the NER pipeline is to increase the data quality in a numismatic database like OCRE. We are able to detect 3 different errors in the coin type record. The first one is called NER1 and represents the situation of not all portraits in the type record are listed. The example here shows a description where the Emperor Quirinus and Carus are mentioned, but only Quirinus appears on the portrait coin tooth. In contrast, the NER pipeline is able to find both emperors here. You can see that here. So, the NER2 error consists of a wrong portrait entry as crown tooth. The example the example's design mentions the Emperor Constantine the Great, but the portrait's record lists his son Constantine II. In contrast, the NER approach result contains only Constantine the Great, which correspond to the design. You can see that here. The last error, named NER3, represents an additional portrait record on the obverse. The example here has a portrait entry of the goddess Diana, who is pictured on the reverse. So she is linked to the obverse, which is obviously an error. But the results of the pipeline show only the Emperor Gallienus as a portrait entry for the obverse. So we can avoid that wrong portrait entry. Oh, sorry, that's the right slide. So, yeah, Diana is here, and she is pictured on the reverse, which you can see here. So this entry here is wrong. So, and we have only Gallienus on the obverse for as a result. So you can see that 3 different errors are brought to light by our pipeline. Therefore, we think that this approach is able to increase the data quality of the OCRE database. So now let's switch to the image recognition. The next subject to discuss are the problems of that approach. A minor problem is the number of results for a single type. Because we have up to 5 classifications results per coin and several coins per type, a comparison query shows many discrepancies on a coin type. This makes a time-consuming manual evaluation necessary. Of course, the image recognition is also not able to identify new classes. At present, not all existing persons in the OCRE database are part of the IR training. The inclusion of all classes would make the whole training process even more time-consuming. But the current incomplete model can bring useful findings too. The example here shows a type with the portrait of Crispina, the wife of Commodus. The largest number of results for this type shows Lucilla, the sister of Commodus. Although this is a good indication of the real person, expanded retraining will be needed to solve this issue. A greater problem is the condition of a coin. For example, we have 39 coins in a poor condition on this example type. One of them is shown here. As you can see, some parts are missing and the portrait image suffered some aberration. The portrait here is Tetricus II. 37 of the 39 damaged coins had a completely wrong top 5 classification. We investigated that problem with the GradCam approach, which provides a heat map with the pixels responsible for the classification. Now you can see that heat map here. This heat map shows 2 major zones of interest, the radiate crown and the chin. You can see them here as the red zones. The model used these zones to classify Tetricus as the second as the Emperor Claudius Gothicus, 29 times. So we think the poor condition of these coins led to this confusion, and this should also be solved in the training process. Our biggest problem with the image recognition approach is the use of the inscription as basis for the identification. We have noticed that problem during a model test with around 500 coin images from the Corpus Nummorum Thracorum database. The results of that test were surprising, because only 25 of 532 images got the correct outcome in the top 5 results. So we generated heat maps for these coins. Basically, it was our intention to train a model that can identify portraits on the coin. Now we could see that a large proportion of the classifications were created due to the inscription, like on this heat map here. You can see it here and here. That would explain the large number of errors, because the model was trained on coins with a Latin inscription from the OCRE database. And so we have here the Greek inscriptions. So there is a problem with this Greek inscription from the CNT coins. Another reason could be the fact that most of the images show plaster casts and not the real coins. So we wanted to trace this inscription problem back to our OCRE data. Another 2 test series with OCRE coins were made, each consisting of 500 images. We could see that the problem here exists as well. The 2 heat maps here should illustrate that problem. The coin on the left with an Augustus portrait shows a partial focus on the inscription, while the Antonius Pius coin has a full focus on it. So you can see the partial focus here, especially here, and the full focus on the inscription is here. In contrast, the third coin has no inscription, and the IR model used the portrait here as base for the classification, as you can see here. You could say that the image recognition behaves like a human numismatist, who also look at the inscription for identifying a coin. But how could this issue be solved? The safest way would be to separate the inscription from the portrait and train the model on that new portrait data. But that would mean that a very time-consuming step would precede the training process. The other possibility would be to move on from the portrait to a type recognition, where the inscription plays a crucial role. So let us move on to the potential of the image recognition. Basically, the possibilities of detecting errors in the OCRE database are very similar to the NER pipeline. CNN error, which matches the NER1 error, in finding additional portraits is one of those. At the moment, the IR model has the problem that we haven't enough coins with 2 or more portraits in the database to train this properly. A wrong portrait entry, which is described by the CNN2 and the NER2 error, can be detected as well. Interestingly, the coin from the NER2 error is identified as Constantine II by the IR model, with a probability of 74%. So, in contrast to the NER2 example, it is possible that the design of the type is wrong, not the portrait, like we had in the NER2 error. The entry of an additional wrong portrait record, CNN3, can also be solved. The results of the IR model for this type do not contain the goddess Diana, who is located on the reverse of that coin. So we can detect that error too. A totally new error named CNN4 describes the issue that the coin has been assigned to a certain type which it does not belong to. The design here describes a bust of Constantinopoulos. The type was assigned one coin which differs a lot from that description. For example, the orientation of the portrait. So it's mentioned here left, and the portrait is to the right. The website of the Const Museum confirms this. The record there identifies the portrait as Julian the Apostate. The second entry of the top 5 results of the IR approach holds Julian. So the model has made an error visible which can't be detected by the NER pipeline. So, as summary and outlook, we can say that our named entity recognition pipeline works well. It is ready to be used as a tool for increasing data quality on numismatic databases. It can find 3 different error types of errors in the data. These errors cover missing, wrong, and additional portrait data. In contrast, the image recognition approach needs more improvement. It's able to find the same errors like the NER pipeline, but it has also some problems. The greatest one of them is the use of a coin's inscription as a basis for the portrait classification. One possible solution for that is to retrain the CNN on coins which had their inscription removed. Training a second network on the inscription data would be an option too. The major advantage of the IR approach is the possibility to find coins which don't belong to a certain type. One problem for both methods is the amount of the manual labor needed for analyzing the, the query data, but this has to be addressed later. A next step for us is to further investigate how a combination of the NER pipeline and the image recognition can assure mutual control. So I now would like to thank you for your attention and want to ask if there are questions.